Welcome back. Now we are going to look at the steady state errors via the steady state error constant or static error constant. So steady state error, steady state error. We are going to look at steady state error. We have looked at it before, but we are going to look at it via the static error constant. Via the static error constant. So we have looked at the steady state error, but we want to define these static error constants. We would like to find that out. In other words, the error performance specifications are specified by the static error constants. So if you recall, for the unit step function, a steady state error was equal to a step. We recall that from a previous discussion was equal to 1 plus limit s goes to 0 GFS. Now this, when limit s goes to 0 GFS, this is actually called the static error constant, and that is defined as Kp. So we can say that Kp is actually the position constant. So this is what we call is the position constant. Kp is called the position constant. Position constant, and that position constant is limit s goes to 0 GFS. So that's the different name. We call it a position constant here. The input is a unit step function, and this is the position constant. So we can write this E infinity step, the steady state error. If you know the static error constant, we can find that by this formula now, 1 plus Kp. And obviously I have to find Kp first, which is the static error constant for the unit step function. So let's take a look at the ramp function now. So for the ramp function, if you recall, what we had for the ramp function was E infinity for steady state, E ramp, and we did this computation before too. It was equal to 1 over limit s goes to 0 s GFS. You recall that, right? So this limit s goes to 0 s GFS is now called the velocity constant, and you write this like that, kv, and this is the velocity constant. And that velocity constant is equal to limit s goes to 0 s GFS. So hopefully that is clear. It's just a matter of writing a different format. The kv is really called the velocity constant. And we can find the steady state error E ramp. So E ramp infinity will just be equal to 1 over kv, which is the velocity constant. But you have to find the velocity constant to find the steady state error. The last but not the least is called the parabolic. Parabolic is the one we are going to label that. If you recall that the parabolic was E infinity and E parabolic. This is all steady state error, parabolic. And that was equal to 1 over limit s goes to 0 s squared GFS. Now this guy, s squared GFS, is called the acceleration constant. So here we go. So Ka, which is the acceleration constant. So we're doing the same thing, but we are first trying to compute this position constant, the velocity constant, and the acceleration constant, depending on the given inputs, such as the unit step, the ramp, and the parabolic. And then after that, we compute the what you call is the steady state error. So the acceleration constant, if you will, is equal to limit s goes to 0, s squared GFS, and once you find that, then you can find the steady state error for E parabolic format. Parabolic, and that is going to be equal to 1 over Ka. So hopefully this you understand this terminology here. We are going to take a look at one more problem to deal with this, and that will close chapter number 7, and then we will start with our design problems. We will look at the root locus and hopefully some frequency design methods and so on and so forth. So I'll see you shortly in the next video. Thank you.